Be just a few minutes here while people are signing in. I'm going to use the restroom, and I'll be right back when we get started. All right. So this is our no doubt. So I would like to pick up today where we left off last time. MAC1140, section 4. And today is the 2nd of September. I believe last time we finished, we were talking about solving equations and inequalities graphically. And we got to talking about increasing and decreasing functions, but we did not get to talk about mins or maxes. So we're going to pick up where we were. We're in section 2.3. I'm going to remind you about increasing and decreasing. And then we're going to talk about mins and maxes. And then I think, are we going to talk about rates of change this week, or is that next week? I'm make sure I'm missing anything that we intended this week. Yeah, we do want to talk about rates of change. Okay, so we got quite a bit today. The increasing and decreasing stuff we talked about last time. The only thing I want to remind you here is that you always give the result as open intervals of x values. So you look along your graph and you ask, where am I going uphill, where am I going downhill? And you make sure that you're giving your answer as an interval of x values, even if the graph has a closed dot. Because at that closed dot, can you say whether you're increasing or decreasing? No, because I can't say whether past that closed dot, you're continuing to go uphill. If WebAssign gives you a hard time about any of that stuff, please let me know, and I'll go in there and try to correct it. Unless we want to talk about something in particular, maybe we should do the mics. So I will go ahead and unmute you, Allison. If you want to ask a question, feel free to unmute. So let's look at a quick example here for the increasing and decreasing stuff. Maybe I have a function that does something like this. I could call this 1, 2, 3, 6. I could say that this height here is 1, 2. And this down here is 1, 2. And this is the graph y equals f of x. So if I wanted to describe where this function is increasing and where this function is decreasing, what we don't want to do is be misled by any information about y values. So if I wanted to split this guy up into pieces, certainly I would say I'm decreasing everywhere on this piece, increasing everywhere on this piece, decreasing everywhere on this piece, and increasing everywhere on this piece. We just have to be careful about how we report that information. I think probably everybody could do what I just did, where you circle the part that's decreasing or circle the part that's increasing. On what interval, this is increasing. This is increasing on the intervals what? Or where is this function increasing? Who could help me out with that? I'll open up the chat here. Remember, you can hold down spacebar to talk if you just want to tell me with words, or you can always type in the chat. Yeah, okay. So I'm happy to see precisely those answers because we need to be a little bit careful. Sorry, on this I guess should be a -2. So remember always intervals of y value, or sorry, intervals of x values. We don't care about the y values. So the function is definitely increasing here, right? And so I smoosh just that part of the function down onto the x axis, and I'll see that my function is increasing from 2 to 4, and also from 6 to infinity. Yeah, so we're definitely increasing everywhere on this interval, right? The 3, we don't turn around and stop increasing for a second or anything like that. The x-intercept has no bearing on whether I'm increasing or decreasing. So we're increasing on the intervals from 2 to 4. And if I wanted to write the whole thing in interval notation, I would say union with 6 to infinity. And the important thing is that we don't get sidetracked by the y values. That's the most common mistake. Similarly, I would say we are decreasing everywhere here. So remember, where is something happening? What's the location of this feature? That's always x values. And the locations at which this function is decreasing we're decreasing along the intervals -infinity up to 2, this guy, and also from 4 to 6. Okay? So I don't think there's anything here that's conceptually too challenging. You just have to remember this little warning that you always give your answers as open intervals of x values. Now, I drew this graph this way because the other thing we want to talk about are mins and maxes. And this graph has some interesting mins and maxes. this x value where we go from decreasing to increasing, that means, well, if I'm decreasing, and then increasing, that means I must have rolled through the bottom of a valley. I had to have turned around. I went from decreasing to increasing. Those are called turning points. A turning point for the function f of x is a point at which the function switches from increasing to decreasing, or vice versa, from decreasing to increasing. And most of the time, these turning points are going to be special features on the graph. Turning point for the function f is a point at which, at which the function switches from increasing to decreasing or decreasing to increasing. So this function has 1, 2, 3 turning points. If I pay attention to just this turning point, imagine I was to zoom in so that my whole field of view was just the little highlighted blue box area there. The very tallest point along the graph is the point 4, 2. That is the maximal value for the function in this local window is 2, and it occurs when x is equal to 4. So we would call that point a local maximum, because locally, that point is where the max value of the function occurs. And similarly, these guys down here, if you were to focus your attention locally, just looking nearby, these guys output the minimum value of the function in that little region. So we would call these guys local minima. So the next thing I would like to do is define for you these two types of extrema. The name for mins and maxes together, these are called extrema. So I'm going to cover up a little bit of this and give you some definitions. If f of c is less than or equal to f of x for all x near c, then we say f has a local minimum at x equals c, and the min value is f of c. So for example, if you look on the graph we've drawn here, f of 2 is -2. And if you look anywhere nearby, if you look in this window, f of x at every other point nearby is bigger than f of 2. So we would say this point is a local min. The min occurs at x equals 2, and the min value is -2. On the other hand, if you turn the inequality around, if f of c is greater than or equal to f of x for all x near c, then we say that f has a local maximum at x equals c, and the max value is f of c. So looking at this point, right here at x equals 4, the output for the function f of 4 is 2. And if you look anywhere nearby, anywhere in this blue box, all the other outputs are smaller. So this point right here, 4, 2, is a local max. And we would say that the max value is 2, and that the max occurs at x equals 4. So just like with increasing and decreasing, the location, the place where something's happening, is always the x coordinate, and the value is the y coordinate. So for the function f graphed above, has the following local extrema. And remember, extrema is the word for mins or maxes altogether. We have a local min. I'll just move left to right. Where is it? It's at x equals 2. And the min value there is -2. We have a local max at x equals 4. And the max value is +2. And then we have another local min at x equals 6. And the min value there was -2 again. Now there is such a thing as an absolute max and an absolute min, rather than a local max or a local min. This function has no absolute max because it continues going up and up and up forever on both sides. But it does have an absolute min. The absolute min is -2, and it occurs twice, once at 6 and once at 2. So I don't want to bore you by writing these definitions again, just replacing the words nearby with everywhere. An absolute min is the lowest point on the graph, anywhere. It's not always guaranteed to exist. Plenty of functions don't have absolute mins. But if there is a lowest point on the graph, then that point is your absolute minimum, and we would say it occurs at whatever that x value is, and we would say that the absolute minimum value is whatever that output or y value there is. Questions about these definitions or this example? Sure. Yeah, let's take a look at one of your homework problems. I don't think you have anything there with absolute extrema, but we can categorize all of the extrema as being local or absolute in addition to finding the local guys. Come on, let us on. So, yeah, they're not going to ask for absolute mins or maxes. We'll have to find one that actually has one of those. Here we go. I'd like to find somewhere they're contrasted, though. Let's see, it might not be so simple to find. The catch is that right now we don't know a whole lot of different functions, and polynomials tend to be a little bit lacking in these features. But let me draw for you a fresh picture, and we'll play around with that. I think I can. Yeah, let's use the reverse side of this first. So maybe here we'll call this like 4, call this like 6. Say this is -1, 1, 2, 3. So this point right here is -1, 4. This point right here is 1, let's say 2. And this point right here, we'll say is 3, 6. Okay, so if this is the graph, let's call it g of x. First, let's categorize any local extrema. Do I have any local mins?
Would it be 1, 2?
Yeah, certainly this point right here is a local minimum, because if I zoom in on that point and I look just in this blue window, that's the lowest that that point gets anywhere nearby, right? That's the lowest the graph of the function gets anywhere nearby that point. So I have a local min at the point 1, 2. How would I describe that? I would say there is a local min at x equals 1, and the min value is 2. And there are no other local mins here, right? There's no other place where the function kind of looks like this. There's no other spot where if you zoom in, if I zoom in anywhere else along here, I don't see myself at the bottom of any valleys or anything like that. What about local maxes? I've got a local max here at -1, 4. Yep, that point's definitely some sort of max. What else? What about this guy? Yeah, he's also a local max. So there is a local max at x equals -1. Yeah, that's correct, Lily. Yeah, at x equals -1. And its max value is 4. Also, there is a local max at x equals 3. And its max value is 6. What about absolute mins? These are also sometimes called global instead of the word absolute, same thing. Are there any absolute mins? Is there a lowest point anywhere on the graph? 1,2 is tempting, right? Because it's a local min and there aren't any other local mins smaller than it. But is this the smallest y value anywhere on the graph? Nah, yeah, like over here we're going all the way down, right? Even this point is lower than this point. So there are no absolute mins. There could only ever be one. Let's be clear about that. There can't be, well, let me think about that twice. No, I'll take that back. Yeah, but there are no absolute mins here. What about absolute maxes? Are there any points here that represent an absolute max?
Yeah, it would be 3, 6, and -1, 4.
Just the 3, 6. Just this guy. Because this guy is not taller than this guy. So the absolute max is a point at which the function is higher than anywhere else. So what I was saying there can only be one of each type, absolute min or absolute max. That's almost true. There can only be one y value. You may hit that y value multiple times. This is a local max, but it's not absolute because it's not taller than this guy. So the thing that makes this an absolute max is that it is the tallest point anywhere on the graph. Nowhere on the graph is there a point higher than him. So here I would say there is an absolute max at x equals 3 and the max value is 6. Now there are some slightly more subtle things that can happen, especially when you start considering functions that are not continuous. I'd like to show you one little example of something like that, but then we need to move on and talk about rates of change. Before we leave this example, are there any questions about how we've determined what points are what, or the language that we've used to describe them? It's very important that you're comfortable with this language also. I mean, your mom didn't leave something on the stove, did she? We're all feeling comfy with this stuff? Okay, let me turn up the heat a little bit. Maybe since we're turning up the heat, I'll call this h of x. apologize. And let's give some names to these things. Let's call this -1. Let's call this -2. Call this height here 1. We can say that this is +1. This is +2. And this would be like 4, 5 maybe. We'll say that this height up here is 3. This height down here is -1, and this height down here is -2. So this is no longer a nice continuous function. He's got all sorts of batshit crazy stuff going on. Can we still identify the mins and maxes? I think so. Maybe I should give us one extra label here. We'll call this -3, and we'll call this height here 2. All right. Local mins first. Where do we see something that looks like a local min? Good, right here. Because if I look anywhere nearby in this window, the point down here is clearly well below all the other y values in this window. So we've got one at 5. Where else? So there is a local min, h of x, has a local min at x equals 5, and the min value is h of 5, which is -2. That's good. Where else? Yeah, good. 2, -1. If I put a little, actually, yeah, for sure. If I put a little window around this guy, then this point is definitely the lowest y value anywhere in that window. So he is a local min. So h of x also has a local min at x equals 2. And the min value there is h of 2, which is -1. So I'm using the function notation there just to try and get us comfy with it, but you could just say that the min value is -2 or the min value is -1. Well, the idea is that the min value at that point is the y value associated with that x value. And I just want us to get more and more comfy with function notation. That's why I'm writing it this way. Okay, here's a question. Local min? Yay or nay? Right here, this blue boxed area. Is this a local min? Good, no, because the value of the function here is not defined by the height of this hole. The value of the function here is way up here. So there's not a local min here. The value of the function here is not the y value of this hole. H of -2 is whatever this is. I guess I haven't prescribed it here. Let's call that 4. So note, there is not a min at x equals -2. Because h of -2 is equal to 4. It's way up there, not the height of the hole. If this was filled in and this was open, then that would be a local min. Right, you want to ask, is the value of the function there smaller than anywhere else in this window? Well, the value of the function at -2 is this guy way up here, the filled in piece. Is this smaller than anywhere else in this window? No, there's all this stuff down here that's smaller. Good, good. Yeah, we got to be a little bit careful. And the trick with that window is, remember, it's really a window of x values. So you can drag it as far down or as far up as you want to. The idea is that you're staying nearby in the horizontal.
What does that last part of the sentence say again? Sorry.
There is not a local min at x equals -2 because h of -2 equals 4, not the height of the hole.
All right,
Sorry.
thank you.
Yeah, I know my handwriting is not at all perfect. Okay, so we have identified the local mins correctly. There's a local min here because that's the lowest point anywhere in this window that I can drag about to. And there's a local min over here because this is the lowest point anywhere in the window about 5. What about maxes?
There's no minimum or absolute minimum, but there is absolute maximum.
That's true. Before we get to there, though, let's talk about local maxes.
Sorry.
No, it's okay. It's okay. What you said is correct. It's good. I'm just trying to go one little thing at a time. So,
will local max be -2 and 4?
good. Yeah. There's not a local min at -2. There's a local max there because this point is actually the tallest point anywhere in this window. So h has a local max at x equals -2, and the max value is 4. And there's another one. Yeah. Benson has it here. Now, I think I intended that height to be 2, but yeah, this is definitely a local max, right? If you look here, this point is clearly the tallest point anywhere in that window. So there's also a local max at -3. And the max value there is 2. What about absolute extrema? And this is what Olivia was getting at a minute ago. Do we have any absolute mins? And this is implied to go off like that forever. Yeah, no absolute min because this piece goes down as far as you want. There is no lowest point on the graph. So there's no absolute mins. Do we have an absolute max? Yeah, the absolute max, you find the tallest point on the graph anywhere, that's this guy. So it occurs at x equals -2. And the absolute max value for h of x is h of -2, which is 4. So the maximum value that this function ever outputs is 4, and it outputs that max value when x is equal to -2. This guy. Questions on this slightly more complicated example? Everybody feeling pretty good? Five comma 3. No, because the value of the function at x equals 5 is down here. So 5 comma 3 isn't even on the graph. There's a hole there. So don't be misled. The holes, remember, that the value of the function at 5 is -2 rather than 3. Yeah, because this is open up here. That indicates that there's not actually a point up there. The point is down here. In order for a point to be a min or a max, it has to be a point that's actually on the graph. So yeah, you'll never get an extrema, either a min or a max, from an open thing like this. It's not just closed dots you have to look at, mind you. Like here, I didn't have a dot drawn in there until after we identified that that was a max. So even without this being drawn as like a thick dot, you could still have said, oh yes, there's definitely a max at -3. But it does have to be a point that's actually on the graph, and holes are not points that are on the graph. Good question. Other questions?
Excuse me, I have a question. That line that's horizontal, like would it, if it were slightly tilted, it would have more local min and max, right?
It depends. So if this guy was slanted down rather than up, and he was filled in at the ends, then those ends would represent extrema, yes. But as it is, he continues off forever and ever like this. So if he was tilted down, then there still wouldn't be any min associated with him because he would continue down like that forever. But if he was slanted down and this point was filled in, then we would have a max there. Does that answer your question?
Yeah, but what about like if it's tilted downwards as you said and it keeps going downwards, and you said that if the starting point isn't filled in, but what about the point that comes like after that one, you know? I don't know if I'm explaining
So
myself.
if this was tilted down, but then instead of an arrow, we had like a closed off point there, is that what you're asking?
I'm sorry, in the other side, when if it's tilted down, if it's still open, like you said, there won't be any local max, even though like
True.
there's points after that.
So if this looked like this instead, I'll draw it in pencil. Please don't add this to your notes because I don't want you to confuse yourselves. If this looked like this instead, then we would still not have a max here because it's open. If this was filled in, then we would have a max here. Make sense?
Yes.
Okay, cool. All right. So I think that's all we need to say about mins and maxes, which means it's time to talk about rates of change. Now, rates of change are of huge importance in calculus. So it's one of the concepts that we really need to get to a place where we're comfy here in pre-calc. First, let me give you the definition. The average rate of change for the function f of x from x equals a to x equals b is f of b minus f of a over b minus a. And this happens to be the same as the slope of the line connecting the points a comma f of a to the point b comma f of b. And the picture that goes with this looks like this. So maybe b is over here, and a is over here. Since we're on the graph y equals f of x, this point right here is a comma f of a. Remember, every point on the graph of a function is some number comma f of that same number. And this point over here is b comma f of b. And the average rate of change for the function on the interval ab, or from x equals a to x equals b, is the slope of the line connecting those 2 points. It's how far you've gone up or down divided by how far you've gone to the right. Most of the time when we think about this, we're thinking about the output as measuring something physical, like a distance. So if the y values for my function are measuring how far you've gone, and the x values are measuring how long it's taken you to get there, then this is a distance divided by a time. And where else have you seen that? Well, if you look on your speedometer in your car, it'll say miles or kilometers per hour. It's a distance divided by a time. So rates of change are speeds. So the rate of change measures how fast or slow the function, specifically the function's outputs, are changing as the inputs change. These numbers can be positive, they can be negative, they can be zero. Thinking about the slope will help it feel a little bit more reasonable. Here you see, if since this point is below this point, even though I've done a little bit of up and a little bit of down over that interval, my overall rate of change is positive because I've done more up than down. So this function from here to here has on average grown because over here the output is higher than over here. It's not grown very fast on average. If I looked from here to here, that line would be steeper. And so I would say that the function was growing faster there than it is here. But it's how fast the output has changed compared to the input. And if you think of the output as being a distance and the input as being a time, then you can think of this as a speed in the sense that you generally think of the word speed as being like miles per hour, or feet per second, or meters per year. Imagine you've got 3 people. So I'll use a fresh page for this. Imagine we have 3 people. Running in a race. Person A, I'll call the first guy. This person runs at a constant speed? Oh shit, sorry, my wife is calling me. Give me just 1 second. Hey, baby. Yeah, I'm teaching. What's up? Okay. 45 what for 10? Tablets? Yeah, that sounds fine. That sounds good. Sure, yeah. Yeah, I'm gonna need a minute here to finish up this class, okay? But then I'll do that. All right, bye-bye. Okay, sorry about that. So person A runs at a constant speed. Person B, so person A's got some wisdom, right? They know they're gonna get tired if they start off fast. But person B is like, okay, I'm gonna go real hard at first and just see how this goes. Do we wanna see this a minute? Yeah, all right, we can come back here. This line, I guess as long as we're back here, this line has a name. It's called the secant line. And it measures how fast the outputs are changing as the inputs change. So as x changes from A to B, how much did f of x grow? That's the idea. All right, so person A is gonna run at a constant speed. Person B runs as fast as possible at the start, but then gets tired, and slows down. Person C, they start slow, saving the energy, and then finish fast. Let's say it takes 5 minutes for person A to finish the race. Over here on the y-axis, I'll measure their distance. And over here on the x-axis, or I'll call it the t-axis, we'll measure their time. Everybody starts off at the starting point. And the finish of the race, I'll call this horizontal line right here. What sort of shape will person A's graph have? If the vertical axis is their distance, the horizontal axis is their time, because they're running at a constant speed, yeah, their rate of change is constant. So the graph of their distance over their time is linear. So this is person A. Person B starts off running as fast as they can. So they start off covering a lot of distance over a short period of time, but then they slow down. So person B, they start off going very fast like this. But then they get tired. Maybe they get really tired, like really tired. Like really tired, and they're just barely moving as they come across the line. We'll call this the graph for person B. And person C, they start off super slow. like barely moving at all, light jog maybe. And then they pick up and they pick up and they pick up and they go faster and faster and faster. So here's the graph for person C. The rate of change for person A is constant. So the amount of distance they cover per unit time is always the same, which means that slope will always be constant. Person B starts off with a really fast slope. They're running really fast. They're covering a lot of distance, a lot of y values over the first few t values. So here they're running very, very fast. Here they're running slower. Briefly, right here for a second, it looks like they're going about the same speed as person A because their slopes are about the same. But then they slow way down and then they're walking and then maybe they're crawling across the finish line. Person C started off very slow, maybe walking, picking it up to a jog, and then going faster. Their slopes are getting steeper. And at the very end, they're going just as fast as person B was at the start. So I'd like to ask a few questions here. Who won the race? A, B, or C? C won the race because they got to this distance, the finish line, at an earlier time than anybody else. B came in last. It took them the longest to get to the finish line, even though they started off going much, much faster. And person A landed right in the middle. They paced themselves. If this is, let's call this here 4 minutes, and let's call this here 6 minutes, what is the average speed of each runner over the whole race? So runner A, let's start with them. I guess we need to give this distance. Let's call the finish line up here. I don't even know what's reasonable because I don't run. Let's call this 200 meters. I think that would probably be hella slow, but I don't have an intuition for this stuff at all. All right, and this is time in minutes. How would I find the average speed for person A? So everybody starts down here at 0, 0. Person C, they finished at 4, 200. Person A finished at 5, 200. And person C finished at 6, 200. You can think of it over distance as distance over time, but I'd like for us to think about it as an average rate of change. So the average rate of change for person A is the slope of the line connecting this point to this point. Since person A's rate of change was constant, it's just the slope of this line. So that's 200 minus 0 over 5 minus 0, which is the same as the distance divided by the time. It's 200 divided by 5. And here, this is measured in meters. And this is measured in minutes. So what is 200 divided by 5? 40, right? So this would be 40 meters per minute. Yeah, that is hella slow. Maybe they're turtles. Right, so you take, we just want to find the slope of the line connecting this point to this point for person A. That's y2, or f of 5, minus f of 0 over 5 minus 0. Person B, theirs would be 200 minus 0 over 6 minus 0. Which is 200 meters over 6 minutes, which doesn't divide cleanly. You can take the factor of 2 in the 6 and cancel it in the top. So that would be 100 over 3, or about 33 meters per minute. And person C, they would be 200 minus 0 over 4 minus 0. Or 200 meters over 4 minutes. I think 200 is divisible by 4. That should be 50 meters per minute. And you see that the person who won the race had the highest average speed. Oops, sorry. It's that last calculation here. The person who won the race had the highest average speed. He didn't always have the highest speed. Down here, he was going much slower than both persons A and B. There was a moment here where he was going about the same speed as person A, and then he sped way up. So these real world problems are a good place to sort of get a feel for what average rates of change mean in the real world. But this being an algebra class, we also need to practice with algebra. So let's do a little bit of that. Before I leave this example, any questions on what we're doing here or how you could interpret this graph? If I just gave you this graph, you could tell me who won, who came in middle, who came in last, who was going fastest at the start, who was going slowest at the start, who kept an average speed, all of those things, constant average speed. Yeah, sure, go ahead, please. So person C here, we got a question about person C. What are we wondering? Or person B? Sorry, that's fine too, yeah.
I have a question about in person B, you know, has C minus 0. Is that a C?
6.
6. Okay.
Yeah, because his time to finish was 6 seconds. Or the difference in x values that goes downstairs in the average rate of change formula would be B minus A, the x2 minus x1.
Yeah, I'm sorry. I thought it was a C.
No, that's okay. I could see how that would be confusing. Yeah, this is a 6.
Thank you.
Mm-hmm. Other questions about what's going on here? Okay then. So I'll talk just a little bit more about this graph to kind of introduce where we're going to go. We can talk about the average rate of change for each of these guys just by calculating the slope connecting any 2 points. These guys all had slightly different average rates of change over the total race, and that's fine. Finding the instantaneous rate of change is a fun challenge that we're not quite ready to attack directly, but we're going to start getting you ready for. The problem of instantaneous rate of change is trying to find how fast any one of these people were going at any given time. Like for person B, what's the slope right here? For person C, what's the slope right here at this point? The way we get there is by coming up with a formula for the average rate of change over an interval whose length we assign a variable to. So the difference quotient and average rates of change. Maybe I have some function here, call it f of x. And I ask you to find for me the average rate of change from this point to this point. And I tell you that this guy is h units away from that guy. And what is the x value here? That would be x plus h, right? Because it's h units to the right of x. So I can come up with a formula for the slope of that line as a function of h. Remember, we're on the graph y equals f of x. So every point is whatever this x value is, comma, f of that thing. So this point right here is x, comma, f of x. This point right here, the x value is x plus h. What's the y value there? It would be f of whatever this is. So f of x plus h. Which means that that difference quotient thing that you guys have been made to work with in the last homework is really an average rate of change. The average rate of change here is, well, it's still f of b minus f of a over b minus a. Here b is x plus h. And a is x. So this is f of x plus h minus f of x over x plus h minus x. And that's your difference quotient. X plus h minus x downstairs, that's just h. This is the difference quotient thing that you've worked with in the past. So the reason we have you working these problems is because in the long run, we're thinking about getting you to Calc 1, where you can find the instantaneous rate of change, which would be the exact slope of the function right at that point. So if I wanted to get at the slope right here, the slope of this thing is always changing. It's a curve. It doesn't have a constant slope. I would take this slope and then make h smaller and smaller and smaller and smaller until I drag this point closer and closer and closer and closer to this point. The downside of that is that the denominator is going to go to 0. So in order to interpret this thing, we're going to need some tricks from calculus. But we won't be doing that in this class. That will be saved for the next class. What we do want to do in this class is get to a place where we can handle the algebra. So if I told you that this was f of x equals x squared, can we find and simplify the expression above for the average rate of change? Well, that would be x plus h all squared minus x squared over h. Right, this piece, if f of x is x squared, if I told you this was the graph of x squared, then f of x plus h is x plus h squared, f of x is x squared, and h is just h. And you would need to FOIL this out. That would be x squared plus hx plus xh plus h squared, that's this first piece, minus x squared over h. You'll see it's the same sort of thing you were doing with the a plus h's in the last homework. The x squareds cancel. This is 2xh plus h squared over h. And you could factor the h from the top. And then cancel it with the h from downstairs. So this would be 2x plus h. So if I wanted to know how fast this function is growing right now at this point, I would plug h equals 0 here. And I learned that the slope of this line, no matter where x is always 2x. And the fancy word for that is derivative. The derivative of x squared is 2x. And you'll see more and more of that as you get closer and closer to Calc 1. And I'll try to drop little references like this from time to time. But this is the connection between difference quotients in the algebra that we did last week and the notion of average rates of change that we're doing this week, and then the concept of the derivative that you're going to meet in calculus. The only catch is you need the concept of a limit before you can really talk about what the derivative is. And of course, we don't do that in this class. That is a calculus thing. But we're getting closer to it, and I'm hoping that you can start to feel the connection. How are we doing for time? Well, I think we're right at time here. So, is there anything that I have not covered? Anything that you guys are going to get in trouble for not having? No, this is all good stuff. I don't think you'll have a hard time with any of these homework problems as long as you take your time and go slow. There's, of course, a thing very similar to the example I did today, only they want you to go the other way. Rather than giving you the information, then drawing the graph, they just give you the graph, and they want you to deduce from that. The other problem that I know you guys are not going to necessarily love, but I'll ask that you be patient with, is this one. So please watch this video and play around a little bit with the things that go on here. The connections that you're able to make right now will go a long way when you get to calculus. And I really want you guys to enjoy that stuff, which means I don't want you to be stressing about what's going on underneath when you get there. So take the time to explore and enjoy these concepts. Work hard on this homework. There's nothing there that should be paralyzing or difficult, but if you do get stuck on anything, of course, you can come by any of my office hours, excuse me, or you can send me a Canvas message. Take a little photo of your work, Send it to me as an email or Canvas message, and I'll give you lots of good feedback on that. Any questions for me before we head out for the day?
I have a question.
Yes, yes.
So Monday, I know it's a holiday, so is the only thing that we need to worry about the homework for Monday?
I'm grateful that you brought that up. So if you look here, you'll see I realized this morning that Monday is a holiday. I changed the due dates. So I extended the due date for this homework to, oh, you can't see it here, can you? This is blocking it. I changed it to Wednesday. So I don't feel like it's fair to have homework be due on a day when we don't meet. So yeah, you can take your time on that homework, but make sure you get it knocked out by Wednesday of next week.
And then I had another question.
Sure, what's up?
So on the exams, will we be allowed to use Desmos? Because some of the homework problems, I needed to use Desmos.
So no, definitely no Desmos, no graphing calculators or utilities of any kind on the exams. There are some graphs I expect you guys to know, right? All the graphs from college algebra I expect you guys to know. So graphs of power functions like x squared, x cubed, x to the 4, x to the 5. Graphs of reciprocal functions like 1 over x squared. Graphs of functions like, we haven't gotten there yet, but e to the x, natural log x. Those basic graphs, square root x, cube root x, those you need to know. And I won't give you anything on the exam that necessitates a graphing utility. But definitely no Desmos, no graphing calculators, nothing like that on the test. If you have to use Desmos for a problem in the homework, and you're uncertain whether that's something that I would expect you to know or something that, due to the nature of the homework, it's okay to use Desmos on, go ahead and ask me. So if there's a particular problem where you're like, I have no idea what this graph looks like, if this was on a test, would I be, what should I do? Then ask me and I'll let you know. Either this is a graph that you should know and you need to know, or this is a problem that's on the homework and I wouldn't put something like that on the exam because it's a little too tough.
Okay, thank you.
No graphing utilities on the homework. Gabriel, that's correct. No homework, no class this Monday. It's Labor Day. It's a holiday that was fought for and won by labor unions because our work is what makes rich people rich and it's deserving of a little bit of acknowledgement. So yeah, Labor Day is Monday and there is no class.
I have a quick question.
Yes.
In the exam, so can we use calculators or not?
The only calculator, so take a look in the syllabus for an answer to most of these. The only calculator that's kosher to use on the test is the TI-32XS, this guy. But nothing else is allowed on the test. So if you want to use a calculator, you're welcome to use this, but you're not required to have it. And I promise I write the tests in such a way that you don't need a calculator. I'm not going to be putting you through any sort of arithmetic or graphing hell that's beyond your abilities. So if you want a calculator, this is the only one that's allowed during tests. The proctors and honor lock will be checking for that. So that's the only option there if you want a calculator.
Thank you.
Of course. Any other questions, guys? Okay, then that's where I'm going to end our meeting for today. I guess I won't be seeing you guys Friday or Monday because Friday we don't have classes and Monday is a holiday. So the next time I'll see you guys is a week from today. That's a long time without anybody yelling mathematics at you. So make sure you spend time yelling mathematics at yourself, at your roommates, at your family, your dog, whatever. Spend time thinking about it. Don't just sit on your hands for the next week, please. That will be very, very bad. Make sure you're working through the homeworks. Take this as a chance to get caught up if you didn't get homework 1 done in time. I'll going through and clearing any extension requests that are in there right now. And if you get stuck on anything, don't hesitate to reach out, okay? Even though there's no class Monday, if you want an office hour or something, just send me an email. We'll figure it out, all right?
Thank you.
All right, you guys have a nice afternoon and a lovely week.